So let me give an example of a two-dimensional vector, and let me, as I do that, I'm going to introduce to you some further notation and terminology, actually, more than notation. So let's look at the vector 2, -3. So first the number 2, then the number -3. We're going to interpret this vector as, again, a directed segment. What does that mean? It means that on the regular xy plane, I'm going to draw a segment that starts at 0, 0 at the origin, okay, and ends at the point to -3. Okay, so this vector moves by 2 units horizontally as it goes from the beginning to the end, and by -3 units, or if you want 3 units downward vertically. Okay. Now, so the tail and the tip of a vector, however, may be different. If I'm talking about the vector 2, -3, that vector doesn't have to start at 0. In fact, remember, that arrow is not a vector. That arrow is a representation of the vector. And therefore, I can represent that vector by making it start somewhere else. For instance, that is also my same vector. I make it start now at the tail. By the way, of course, by tail I mean the beginning point. And so I make it start at -4, 4, and then I make it stop at -2, 1. Okay, so if you notice, this arrow also, of course, you can see it visually, this arrow also moves as it goes from the tail to the tip, moves 2 units horizontally to the right and 3 units vertically down. Okay. Now I can also put that arrow, that representation of the vector, anywhere else I want, starting at any point x1, y1, which would be my tail, and stopping at any point x2, y2, which is going to be my tip. Okay. However, if I do that, I cannot do it just any which way I want. I have to make sure that if the tail is x1, y1 and the tip is x2, y2, then the vector that I'm looking at, v1, v2, has to be given by, first number is the difference of the x coordinates, second number is the difference of the y coordinates. Now you may notice that I'm calling those two numbers the first number, the second number, and I hope you're starting to feel the need to actually give a special, specific name to those two numbers. That's coming. I just want to generate a little bit of desire in you to have this new word coming. So now this is a very simple example of 2D vector. I'm not going to dwell on it much more because you're probably very familiar with this stuff. So we're going to move on and just give you a little bit of a preview of what's coming next. So how are we going to use vectors? How are we going to use vectors in the course? I mean, what are we going to do with them? Well, this is the plan fraction for how we're going to be studying vectors. We're going to start by defining them in a familiar setting, just as we've done for 2D vectors. Of course, 2D vectors are just the very beginning. We're going to extend this idea of vectors to other kinds of vectors. Okay, but we're going to start in a familiar setting like this one. Okay, and then we're going to develop some basic useful properties. For instance, once we start with those two vectors, u and v, we can think of adding them. We're going to define a very logical, very useful way of adding those two vectors. We're going to define a whole bunch of other operations and see why and how they're useful. Okay, so we're going to start basically building on these basic blocks of familiar vectors. And then what we're going to do is we're going to extend their definition. Okay, so we're extending not only in terms of using more numbers, not just 2 numbers, but 3 or 4 or 5 or whatever many you want. Okay, but also we're going to extend them in both directions. We're going to start considering sets of numbers organized in some kind of rectangular array, which we're going to call a matrix. And we're going to, what? Derivatives? Vectors? What does that have to do with it? Remember that calculus 212, your basic course, was a prerequisite for this one? Well, that's because functions are going to be seen at some point as vectors. How? Just hang on to your hat, we'll get there. Okay, but we're going to extend the definition to other similar situations. Okay, and there we're going to explore from that what else can we do with them. So what is common to all these extended definitions and what is common that we can use that becomes useful, right? So I'm going to leave you now for this class with these questions for you to ponder, questions that we're going to revisit in later classes. Things like, for instance, can you define a 3D vector? I'm sure you can, and we're going to see that very quickly in the next class. Okay? But can we define a high D vector, a high dimensional vector? Well, probably that's not very difficult for you either, right? So we're going to look at some of those definitions very quickly. But then, here is a little challenge for you. Can you define a vector that has nothing to do with sets of scalars? And yeah, I've given you the example of derivatives or maybe functions, but in what sense are they vectors? Can you think of why would we consider them as vectors? What do they have in common with ordered sets of numbers? We'll look into that. So stay tuned, and we're going to explore all these issues. We're going to find out how to explore them and what kind of knowledge to gain and how to play with these things to discover big, great, and wonderful ways of analyzing very applied concepts.